Today, my talk is going to be on exploring the metaverse with graph deep learning. Okay, so obviously the term what I call the metaverse is a play on the metaverse that a lot of the Silicon Valley companies are talking about. While of course, when they are talking about the metaverse, they are really talking about the virtual world. As material scientists, we are really interested more in the physical world and the materials that actually make up our physical world, right? So this graph here basically shows the way that I like to think about the metaverse, right? Which is that we can always think about the metaverse in terms of things like chemical complexity and structural complexity. So when we think about very, very simple materials, so for example, the things that we all learn in high school, like our FCC metals, VCC metals, they fall in the bottom left corner of this two axes, right? So they are both chemically simple and they are also structurally very simple, right? Now, as you know, today one of the hottest topic is high entropy alloys, or what is called multiple principal element alloys, where you really just try to squeeze as many different types of elements together in the same lattice. Here we really have a lot of chemical complexity, but less structural complexity, right? Now, of course, the whole metaverse is made up of materials all across the range of chemical and structural complexity, right? So on the top right-hand corner, we have things like our polycrystalline materials, which are really what we get in the real world, where we have both chemical complexity as well as structural complexity in the form of grain boundaries, as well as interfaces and surfaces and that sort of thing. Now, one of the holy grails in computational material science is to be able to model this entire metaverse in a way that is as efficient and as accurate as possible. Now, the problem, however, is that our techniques that we have today, the computational tools that we have, are not able to do that, right? So we have our very accurate ab initio methods, which are very transferable. So you can actually model any type of chemical complexity with it. However, because they are so expensive, you usually cannot access a lot of structural complexity, right? So for example, if you are to model this polycrystalline high entropy alloy, that is not going to be possible, at least with current DFT techniques. Now, on the other hand, we have our interatomic potentials, which are much more efficient, but because we usually fit them to just one narrow chemistry, they can only access very limited chemical complexity. Okay, so of course, the organic molecules are very well established in terms of applying interatomic potentials for their modeling of what they call force fields. We can also build force fields for things like simple metals or binary alloys and certain types of system. But by and large, traditional force fields is actually very hard to access chemical complexity with them. Okay, so the structure of my talk today is based on how do we go about accelerating the way that we do computational materials design using graph deep learning, right? And the way that I like to think of this problem is how do we actually usually do computational materials design? We usually first have some candidate structure, right? So you either come up with it by imagining this crystal structure, or you get it from substituting from existing known structures, okay? And the next step is that you're going to do equilibrium structure relaxation, in which you basically want to get you relax the structure to the lowest energy possible positions. For that, you actually need to know what is the energy or forces in the structure as a function of the atomic positions, right? Then after that, you usually then do a separate property computation to get the property that you need. Okay, so it can be things like the band gap, the bulk modulus, or whatever property that you need to design your material for the application that you're looking at. Okay. So today, of course, the easiest way to do this is through DFT calculations, and we can already do it in high throughput. So we can already run DFT across tens or thousands of materials, And we do DFT to relax the structure, and we then use DFT to also do property predictions, okay? Now, however, this kind of this high throughput DFT is actually not enough, right? So this is a chart that I like to show. This shows you the data history of the materials project. So the materials project has been around since 2012, and since its inception in 2012, the amount of data in the materials project has grown steadily until the present day, right? And what you notice immediately from this graph is that the number of structures in the materials project has stagnated at about 140,000 materials in recent years, okay? So really, we do not actually have we have not seen much growth in the total number of structures for quite a number of years. And also some of the data sets that we have, so for example, things like computed phonons or the elastic tensors, they are much smaller in data size in comparison to things like structure and energies, okay? So, and the reason why that's the case is, of course, computing things like elastic tensors are a lot more expensive compared to running just standard DFT energy calculations, okay? So what we really need is a way to speed up this process, right? And for the first part of my talk, I'm going to talk about how we can actually replace some of the DFT property predictions with machine learning based property prediction, okay? So the type of machine learning models that my group likes to work with are what are called material graph networks, or in the literature, people also call them graph neural networks or message passing neural networks, okay? So the reason why they are called that is graphs actually turn out to be a very natural representation for materials. You can think of the atoms as the nodes in the graph and the bonds as the edges in a graph. And each of these nodes and edges are represented by a vector of numbers. Now, in the materials graph network architecture, we not only have the bonds, the nodes and edges, we also have what is called a global state vector. This is actually a very important feature of our architecture because this allows us to do some things which are not possible with other types of graph neural networks, okay? Now, basically, the way that the graph neural networks work is that you perform a series of update operations. So for instance, in the first step, you can update each bond with the information from the atoms that are forming the bond, okay? So in this case, for example, EK1 here, you actually update it with information from VRK and VSK. Now, this is via what is called a bond update function, and then you can imagine that in the next step, instead of just going through all the bonds, we now go through all the atoms and we update the atom information with information from the bonds that are connected to it, and we also update the global state with information from all the bonds and edges as well. So this three-step process is what we call a materials graph network block or a magnet block. Okay. Now, by stacking multiple magnet blocks, we can actually create models that can then predict, which can then be trained on any property that we want to predict. Okay. So it turns out that material graph networks or magnet models are actually extremely effective. So these are some of the mean absolute errors of magnet models that we have trained on the properties of crystals that are in the materials project. So we have built magnet models that can predict things like the formation energies, the band gap, the log of the bulk modulus and shell modulus, and also classifiers to classify whether a material is a metal or an insulator. Now, I want to focus on a few properties here. So if you think about the formation energy, for instance, the magnet models that we train can predict the formation energy to up to a mean absolute error of 28 MeV per atom, right? And this is actually on par or better than most of the machine learning models out there for the formation energies, okay? And just to give you a sense of whether this 28 MeV per atom is enough, there's this work that was done by Wenhao Sun back in 2016, where he looked at basically what are the energy above the ground state for all the structures in the inorganic crystal structure database, right? So most of the crystals in the ICSD have actually been synthesized. So if we look at all these structures, we find that about 80 or 90% of those structures fall within this 100 MeV per atom threshold above the ground state. So if we can predict the formation energy with an accuracy of about 28 MeV per atom, this is already well within that limit. So in other words, we have sufficient accuracy that we can actually guess or at least give a good prediction of whether a material is likely to be synthesizable or not. Okay. Now, we can, if you look at the band gap predictions, we get about 0.33 EV, which is also quite good. And then we also have things like the Bow and Show modulus, which are on par with the state of the art. Okay. Now, one of the problems with magnet models, however, or with graph neural networks in general, is that they tend to be very data hungry. Okay, so, and you notice that basically in terms of data set sizes, we have very, very different data set sizes, right? So that can be a challenge for some of the model accuracies. Okay, so in the next part, I'm going to show you how we can actually adapt our materials graph network models to actually handle one of the key problems with materials data, which is that of the trade-off between data quantity and data quality. Okay, so one of the truisms in material science is that high-value data. So what we mean by high-value data is things like very, very accurate calculations or very, very good experimental measurements of data materials property. Tend to be scarce, right? So they are difficult to do and they are expensive to do. So they tend to be, the data sets tend to be small. So one of the classic examples is the band gap, right? So today we can do DFT calculations using the PBE functional, and we already can get things like about 50,000 band gap data points, right? So this is a very, very good and large data set. However, PBE, as we know, the PBE functional is also one of the most inaccurate and the least valuable in terms of band gap accuracy, right? So we all know that the PBE functional tends to systematically underestimate the band gap. Now we can do more expensive HSE calculations, but because HSE calculations are so expensive, the data set sizes are much smaller. And for experimental data, there is even smaller, right? So there's only about 2,700 band gaps that we have found in the literature, okay? And of course, all these smaller data sets are what we actually want to predict. There's no use predicting the most inaccurate data point, even if we can predict it to very high precision, right? So how do we actually adapt our magnet model to actually predict this high value data? So the way that we do this is using what is called multi-fidelity graph networks. So remember that global state that I mentioned before. So we can use this global state to actually embed information about the fidelity of the data. So for example, we can assign a fidelity of 0 to the PBE, HSE, we can assign a fidelity of 2, and experimental data, we assign a fidelity of 3. And then we use that to label all the data, whether this is an experimental band gap or HSE band gap or PBE band gap. And the rest of the architecture of the graph network actually remains the same. And does this work? What we found was that, okay, so this is the orange bar shows you the mean absolute error in the band gap if we train on just each of the data set by themselves. So for example, for the PBE data, we can get within a mean absolute error of about 0.3 EV or so. However, what you notice is that the mean absolute error for the HSE data and the experimental data is actually significantly higher. And that is really because the data set sizes are also much smaller. However, because with our multi-fidelity magnet models, we can actually train 2-fidelity and 4-fidelity models. In other words, we can just throw all the data together and build one single model that predicts any fidelity. We can actually significantly improve on the predictions of our HSE and experimental band gaps. For example, by just combining the PBE data with one of the high fidelity data, like for example, HSE, we can already reduce the mean absolute error in the prediction of the band gaps by about 40 to 50%, okay? Same for the experimental band gaps, right? So whenever I show this data, a lot of people are wondering, whoa, how come this work, right? Because we are not actually increasing the amount of HSE data or experimental data, but somehow we are actually getting much better performance on the HSE and experimental data. And the reason is because even though the PBE data is relatively inaccurate, with a large PBE data set, you actually significantly improve the latent structural features such that you have a good separation of high bandgap and low bandgap materials. And it is this improvement in the latent structural feature space that we believe is responsible for the improved performance on the HSE and experimental bandgap data. Okay. All right. So with that, I hope that I've convinced you that today machine learning property prediction is a reality, right? So with materials graph network models, we can predict quite a number of properties to fairly good accuracy, and we can already use them to make decisions about what materials we want to pursue for our next step. So whether it is experimental synthesis or something else, right? We still have a bottleneck, right? So one of the main weaknesses of graph neural networks is that you need the input graph. And the input graph, you usually obtain it from the DFT relaxed structure. Now, if I have to do a DFT relaxation, that kind of defeat the purpose, right? So now my pipeline is no longer bottlenecked by our property prediction, but it is now bottlenecked by my DFT structure relaxation. So what we really need is to replace this DFT structure relaxation with machine learned structure relaxation, okay? So we actually explored a few ways to do this. Okay, so the first way is just by applying the variational principle with using our formation energy magnet model, and by using Bayesian optimization to relax the structure and finding the lowest energy structure, we can already do a relaxation of the crystal structure, right? And we can actually show that this kind of Bayesian optimization process can significantly improve the machine learning property predictions, and then we can then use those predictions to actually do material screening, right? So just to show you an example of a success story, so there's this work that we perform where we try to look for ultra incompressible hard materials. The way that we do this is that we started from about 5,500 structure prototypes. We do various substitutions to get about 400,000 candidate structures. So this is a very large number of structures which you can't actually do just pure DFT screening on. What we then do is that we use our Bayesian optimization algorithm to relax the crystal structure, and then we screen based on machine learning property predictions. And then we narrow down the candidates to about 1,000. And then finally, we just do DFT calculations on 1,000 structures to get about 143 potentially stable structures. And finally, our experimental collaborators, the group of Professor Xian Luo, went ahead to try to synthesize 8 of them. And we actually managed to get actually all 8 new crystal structures. Here are 2 examples of completely new crystal structures, one rhenium tungsten boride and one molybdenum tungsten carbide. And they actually have structures that are in very, very good agreement with the experimentally measured structures. So these are the XRD patterns. And also they are measured bulk and shear modulus are in very good agreement with not just the DFT verifications, but also our machine learning model predictions. Okay, so this is one of the rare examples where we show that you can actually go from a machine learning, pure machine learning structure and property prediction to DFT structure and DFT property prediction, and finally to experimental synthesis and verification. Okay, so the entire pipeline is actually closed and verified. All right. So the other way of actually relaxing a crystal structure is using interatomic potentials, as I mentioned in my very first slide, right? So today, people have also used machine learning to develop interatomic potentials. So machine learning interatomic potentials usually express the potential energy surface as in the form of some local environment fingerprint. So there are many different variations. So things like the neural network potentials, the Gaussian approximation potentials, or spectral neighbor analysis potentials, and they all express your local environments in terms of things like the symmetry functions, which looks at the distances and angles between atoms, or things like the neighbor density. Okay, now the specifics of the machine learning interatomic potential is not too important for this particular talk. What you need to know is that all the machine learning interatomic potentials have been shown to be to significantly outperform your traditional EAM and MEM potentials in terms of things like predicting the energies as well as forces. Okay, so the problem, however, is that while machine learning interatomic potentials has been a great success story of the application of machine learning in material science, you actually can't use them effectively for materials design. Okay, so there are a few issues. First of all, the number of turns actually tends to grow actually grows combinatorially with the number of elements. So, for example, if you go to like 4 or 5 or 6 elements, then the model becomes very unwieldy for at least in the traditional formalisms. And then you basically have to custom fit each machine learning interatomic potential for each system or chemistry of interest. And with that, you basically can't use it for broad-based materials discovery. Okay, what we have done is really we have thought about using our magnet models and adapting it to build a universal potential using a graph-based representation. Okay, so we took inspiration from our traditional interatomic potentials, and we basically augmented our materials graph networks with many body terms. So instead of magnet, now we have what is called M3G net, which is a materials graph with 3 body interactions. And using this new architecture, we can now begin to train a universal potential that works across the entire periodic table. Okay. Now, to do this, we basically rely on underutilized data in the materials project. So the materials project has performed about 100,000 plus DFT structure relaxation since 2012. This gives us about 100,000 energies, about 10 million forces, and about 1 million stresses. And it actually also covers about 89 elements of the periodic table. Okay. So what we did was that we basically took all this data and we threw it into our M3GNet model and trained a universal potential that can work across all 89 elements. Okay, so this is actually the performance metrics. We can actually achieve energy error of within 33 MeV per atom. So this is extremely good. So just to reiterate, these are for the entire periodic table, and it actually works universally across all structures and all chemistries. Okay, the force errors are also very reasonable, 0.07 EV per angstrom, and the stress performance not so great, but that's mainly because the training data does not have very well converged stresses to begin with. Okay, so with this M3GNet universal potential, what we can do today is to do DFT-free relaxation of crystal structures. Okay, so we actually have a test data set of about 3,000 structures with DFT relaxations. And what we show is that basically for these 3,000 structures, we can actually get predicted ground state energies that are very, very close to the DFT ground state energies. And the relaxed volumes of our crystals are also very, very close, typically within 1 to 2% of the DFT final relaxed volumes. Okay. With the energy predictions, we can also make stability predictions. We can do things like calculating the stability of hypothetical crystal structures that we generate, and we compare that. We chose the top 1,000 to compare that with DFT calculations, and we actually can show that in general, the distribution of the predicted E above Hall is actually very similar between our M3GNet predictions as well as our DFT predictions. Okay, beyond just predicting energies and doing structural relaxations with universal potential, you can then do dynamic calculations as well. You can actually simulate things like the phonon dispersion patterns, and we can actually show that the predicted phonon dot centers are again in very, very good agreement with what you get from DFT. We can calculate things like the bulk modulus, and we can even run MD simulations to get things like the ionic conductivity of a material. So here we show the example of Li3YCl6, which is a very famous lithium superionic conductor. And you can see that the predictions from our M3GNet universal potential is actually in fairly good agreement with what you get from an AIMD simulation. Okay. Now, with that, we have already begun to use this universal M3GNet universal potential to build what we call the Matterverse.ai database. So this is a complementary database to the materials project. So the materials project will still remain a DFT-based database. For Matterverse.ai, what we envision is a machine learning based database. Okay, so we are looking at using M3GNet to predict relaxed crystal structures. And our target is, instead of just 140,000 materials, we want to really generate millions and billions of materials. Okay, and we also would include things like machine learned property predictions as well. Okay, so the current progress, we have already generated about 31 million structures, out of which about 1.8 million have an E above power of 0. Using this entire data set, we are performing a massive scale search for new lithium superionic conductors. So this is just one of the initiatives that we are looking at. We can actually show that the predicted ionic conductivities are actually so good that we can actually identify a regime where all the good ionic conductors actually sit. So there are still a lot of unexplored points over here that we can explore for new lithium superionic conductors that potentially can be good solid electrolytes for all solid state batteries. Okay. All right. So this is the Matterverse.ai website. So if you go to Matterverse.ai, you can actually play around with it. You can do a searches. And for example, if you look up a material, what you see that we have predictions of not just the formation energy, band gap, but also things like the experimental band gap and the HSE band gap, which is from our multi-fidelity magnet models. Okay. All right, so to conclude, using natural graph representations, we can actually build universal machine learning models for material science. We can use them for property prediction. We can also use them for interatomic potentials, okay? And machine learning accelerated materials discovery is a reality. So it has been demonstrated. So as I shown in my example of the ultra incompressible materials, and we have built this universal potential formalism that called M3GNet that is very, very robust. I actually only showed a fraction of the validations that we have done. I welcome everyone to try it out and test it. And if you find any problems, do let me know. And right now, all that we are constrained by is just the accuracy of the input DFT data. Okay. So with this, I just want to acknowledge that most of the work is done by my previous project scientist, Chi Chen, and funding comes from the Department of Energy under the Materials Project. And as usual with all my group's work, all our software is open source on GitHub. You just need to go to our Materials Virtual Lab organization, and you can play around with any of the codes. And they have lots of examples. Okay. And thank you, and I'm happy to take any questions.